So in this video, I want to explore the concept of unit generators, which is a fundamental concept we need in order to create our own synthesizers and signal processors. I first want to look at this notion as it relates to modular analog synthesizers, and then I want to show how it has been influential in the development of computer music languages. So let's start with these analog modular synthesizers that look something like this. This is a Moog 55 that was first released in the mid-1960s. And what you see here is the way that sound is created on these modular synthesizers is through a series of modules. So like this is a module here, this is another module here, and that's another one, and so on and so forth. Each of these is a module. And each module has a series of audio ports on it. Some are inputs and some are outputs, and a bunch of knobs that let you control different parameters of how it's working. And so each of these modules in and of themselves tends to do a very simple task. One might make a sine wave and have knobs that let you control the frequency and the amplitude of the sine wave, for instance. But when you string these together by literally plugging in different cables to connect the inputs and outputs together, and you tweak these knobs to particular settings, you can create some incredibly interesting and rich sounds as a result. And to show you how that works in practice, I thought I'd show you a video from Richard Devine. You may remember that a bunch of the sounds that are bundled with the EarSketch software that we've been using throughout the course here were created by Richard Devine for us. And a number of them he actually created using analog modular synthesizers, not so different from this one. So I thought I'd let you watch a video of Richard performing on a modern day modular system. And so you can see how he's connected everything together and how he's tweaking things live in order to create some, what I think are some pretty fascinating and incredible sounds. I should point out that obviously the Moog in the picture here was made in the 60s, but there's been a resurgence of interest in these modular synthesizers in recent years, and there's a number of manufacturers that are making these things new today. And so when you watch Richard's video, the modules that he's actually using are not vintage ones from the 60s or 70s. They're brand new ones that were just made in the last couple of years. So some basic types of modules you might find are things like a sine oscillator, a white noise generator that makes white noise, a low-pass filter that filters sound the same way that we looked at low-pass filters in Module 2. An adder that takes two input signals and adds them together, mixes them basically into a single output. A multiplier that might multiply two input signals together instead of adding them. An echo that might delay sound a certain amount of time. There's many other examples as well, but these are some basic ones that we're going to keep on coming back to again and again throughout this module. And so when we look at computer music languages, which started to develop around the same time as those modular analog synthesizers, the first ones were being developed at Bell Labs by Max Matthews, and they're called the Music N languages. And none of them were actually called Music N. They were called Music 1, and then Music 2, and 3, and 4, and 5, and each one kind of came a year or two after the previous one, and so that's why we call them collectively the Music N languages. One of the key concepts that emerged over the course of developing these Music N languages, as Max Matthews was at Bell Labs, was this notion of a unit generator. And it's a parallel idea to this module in analog synthesis. It's a computational unit that does something very simple and has a certain number of inputs and a certain number of outputs for audio, but then it also has a certain number of knobs, which we often call parameters, that let you tweak different behaviors about what it's actually doing. Like the frequency or amplitude of a sine oscillator, for instance. And so Max came up with this notion of using unit generators inside of a computer music programming language to make it easier to kind of string these things together to make music. And this is such a powerful idea that pretty much just about every computer music language that's out there today still uses this notion of a unit generator. We also sometimes abbreviate it as a UGen. So when I get lazy throughout these videos, I'll start saying UGen instead of unit generator, because I guess I just want to save some time. So I wanted to say a couple more words about this pioneering work that Max Matthews and others were doing at Bell Labs. at the time they were developing these languages. They were working on mainframe computers, obviously, very different from the laptops we're used to today. And they were using punch cards to encode programs. The audio was not getting generated in real time. Often it would take hours to compute just a second or two of digital audio. But the results were really capturing people's imaginations at the time. I want you to watch a quick video of the song Daisy Bell being synthesized at Bell Labs. And so you'll hear some speech synthesis, which was another research area going on at Bell Labs at the time, singing the words to Daisy Bell. And then you'll hear an accompaniment with the chords. And the accompaniment is what is being synthesized using one of these music N languages. You may recognize Daisy Bell from another context. This song was sung by HAL in 2001: A Space Odyssey, and that happened because Arthur Clarke had heard about what was going on at Bell Labs, and I think actually seen a demo, and was captivated by that, and so incorporated that as a plot element. Now there's a number of different computer music languages out there today. There's probably hundreds of them out there. I just wanted to highlight a few of the most popular ones here for you, and give you a sense of how they're different from each other. MaxMSP is one of the most popular ones out there today. It's a commercial program that's best known because it's a graphical environment. So in MaxMSP, each UGen is actually represented by a rectangle on your screen, and each of those arrows is represented by a line that connects different UGens to each other. Pure Data is based on the same concept. It's very similar to MaxMSP. It's an open source program. And SuperCollider is another very popular environment. It's also open source. And it has a text-based syntax, so you program with text. Its syntax is very similar to a programming language called Smalltalk. And it also has a kind of unusual setup in that when you actually execute this code to make sound, you send it from a client software program to a server software program, which actually interprets the code and makes it into sound. These are typically on the same machine, but they can be in different locations, and there's different things that are enabled by the fact that these two activities are separated from each other. Chuck, an open source language developed at Princeton and Stanford, is known for its very strict timing, so you can have a lot of different things going on at once, and they can all stay in perfect synchronization with each other. Its syntax resembles pretty closely the programming language C or also Java. And C Sound is another language which, despite the fact that it has C in its title, is actually nothing like the C programming language. It's most close to the music N languages, and it's the most direct descendant of them that's still used today. So I just want to point out these different languages and some of the differences between them, so that if you want to explore further beyond the Python and the EarSketch system we're using in this course, you have some suggestions for some good places to start. So in Module 5, we took the basics of algorithmic composition of the EarSketch API and of programming in Python that we learned in Module 4, and we took it to the next level. We looked at ways that writing code can fundamentally change your perspective on creating music. And we did this by looking through at a number of different techniques, at data sonification, at chants and stochastics and the difference between them. We looked at process music, and we also looked at musical modeling. And then we looked at this in terms of historical examples of composers that have been pioneers in each of these areas, people like Hiller and Isaacson, John Cage, Xenakis, Reich, Cope, and Francois Pache. And then at the end of the module, we took a little bit of a turn and we looked at a kind of lower level of abstraction of dealing with audio and audio samples at a lower level in terms of digital signal processing and synthesis. And we considered this whole process in terms of the idea of modular synthesis, the notion of a unit generator, which is the foundation of digital signal processing in many modern computer programming languages. As we move towards Module 6, we're going to kind of move out more broadly as we close this course and really look at the cutting edge of music technology, how we can take everything we've learned in these first 5 modules and how these ideas are being expanded and extended in industry and academia today to really transform the ways that we create and experience music.